Hello everybody, Gadget Boy here. We're going to take a break from our usual technical DIY videos and do a little bit of math. Now before you run away, it's fairly simple math. I just want to explain engineering notation so that you guys have a more thorough understanding of what I'm meaning when I talk about kiloohms or megohms or picofarads, etc., etc. So engineering notation is pretty important to us sciencey types because it allows us to condense very large numbers into a more succinct. Hi, cat. Sorry, she's twining around my feet. I got distracted there for a second. Anyway, it allows us to take large numbers and condense them to smaller, more succinct, easier to understand numbers. And each of those comes with its own specific engineering notation multiplier. Now, when you start with your base unit, you don't modify your base unit. It's just the unit. So we're going to put that here on about the middle of the page. The base unit is 1 times 10 to the 0th. I don't even know if 0th is the right term, but it's 1 times 10 to the 0. And that doesn't do any modification to the number that you have. It just makes the number that's sitting in front of you. Now, for the next unit, we're going to go down first. The next unit is milli. And that's typically notated with a lowercase m. Actually, it's not typically notated with a lowercase m, it is notated with a lowercase m. And that's going to be 1 times 10 to the minus 3. So that shifts the decimal point to the left 3 points, or 3 zeros. Now, the next one that we're going to look at is micro. And that's 1 times 10 to the minus 6. And that's notated with this little fancy lowercase u. The next one down is going to be nano. That's 1 times 10 to the minus 9. Noticing a pattern here, that each of these increases by 3 for each increment that we're going. And I'll get more into why that's significant in a second. And of course, nano is just notated with a lowercase n. Now, we're starting to get into the stuff that we're starting to get out of the range of what you'll normally get into with your hobbyist electronics, but we'll keep going all the way down just so you can see what they all are. So the next one is going to be pico, and that is 1 times 10 to the negative. Anybody guess? 12. And that, of course, is notated with a lowercase p. And then the next one is going to be femto. I've never used femto notation. I know there are probably femtofarad capacitors out there somewhere for like really high accuracy applications, but I've never run into any piece of electronics equipment that uses, or electronics componentry that uses a femto anything. But there it is anyway. And that's going to be 1 times 10 to the minus 15th. I'm sure you're probably guessing what the next one on these is going to be by now. And that predictably is notated with a lowercase f. The next one is, I always get these mixed up. This one is atto. and that's 1 times 10 to the minus 18, and that is notated with a lowercase a. I'm getting kind of off-center here, but we'll just keep going. The next one is zepto, which just sounds kind of fun, so that's going to be 1 times 10 to the minus 21, and that is notated, I'm sure you guessed, with a lowercase z. And the last one, which is the kind of funny sounding one, is yocto. And that's 1 times 10 to the minus 24. And is notated with a lowercase y. I don't know of any beyond that. When you're looking at the 1 times 10 to the negative 24th, you're talking about something that is 1 septillionth of the whole thing. It is so ludicrously microscopically tiny. I don't even know what a yocto notation would be used for, unless maybe in like quantum mechanics when you're dealing with stuff down at the atomic level, but we don't deal with that. Generally, our experience with these notations stops at pico, when you're dealing with picofarad capacitors. We won't see anything smaller than that. Now, going up in the other direction, now we want to get big rather than getting small. So the next, when we're getting bigger, the next largest unit from your base unit is kilo. And I'm sure you've probably guessed that's going to be 1 times 10 to the positive 3. And it is notated with a lowercase k. Now they don't use an uppercase k for this is because Lord Kelvin stole the uppercase k for his temperature notation, so the scientists decided they were going to use a lowercase k for the kilo notation. Then the next one up from there is mega. And that's 1 times 10 to the 6th. And that is notated with an uppercase M. And then the next one up from there is giga. Now we're all used to megabytes and gigabytes. And that's 1 times 10 to the 9th. Keeping in mind that gigabyte is actually 1024 times 10 to the 9th bytes, but generally when you're looking at them in stores, they just round to the nearest thousandth, which actually means you get shorted a little bit on your hard drive sizes, because if they say that it's 100 gigabytes, they're talking about 100 times 10 to the 9th, whereas an actual gigabyte is going to 100 actual gigabytes is going to be 102.4 times 10 to the 9th gigabytes, but they get away with it for some reason. Anyway, so that's notated, of course, with a capital G. And we've actually exited the realm of numbers that you're going to deal with in standard hobbyist electronics when we left mega. I don't think I've ever dealt with anything in the giga range electronically. I'm sure there are gigohm resistors out there somewhere, but I haven't seen anything like that. And then the next one up is tera. We're starting to get into terabyte hard drives now. That's 1 times 10 to the 12th. And it's notated with a capital T. I'm starting to curve off here. I should have used lined paper or something. Next one up is peta. And that's 1 times 10 to the 15. And that, of course, is going to be notated with a capital P. Next one up from there, I actually have to consult a chart here because I'm starting to forget. Oh right, EXA. I should have remembered that. Exabytes. If only we had an exabyte hard drive, that would be awesome. And that's 1 times 10 to the 18. And that, of course, is notated with a capital E. And from exa, we go to zeta. And that's 1 times 10 to the 21. And is notated with a capital Z. That Z is really messed up. Oh well. And then, last but not least, is yotta. And that's 1 times 10 to the 24th. And that, of course, is going to be notated with a capital Y. So we've gone all the way up and all the way down. Now, like I said, we're not going to go any higher than about megohms or mega notation in base electronics, and not much smaller than pico. Now, this is really important, and I'm just going to turn my paper sideways here so we can use the extra white space here to talk about why we use engineering notation. Now, let's talk about internet routers. We'll touch on those real quick. You'll notice that they have, most modern routers now have a 5 gigahertz bandwidth that you can use. It's supported by most devices. And that 5 gigahertz is 5 0 0 0 0. So it's 5 billion hertz. Now, rather than writing 5 billion hertz, we can just go 5 gigahertz. And it's much easier. Now, there's no real easy way to memorize these. All you really have to do is remember what order they go in, because if you can remember what order the notations go in, all you have to remember is that it increases by 3 for the multiplier each time. Now another, I mentioned earlier that the fact that it increases by 3 each time is significant, and I'll actually use my example here. You'll notice that we put a comma every 3 zeros. So every thousand multiplier, we get a comma or an increase in the multiplier on our engineering notation. This is useful when you're trying to decipher the value of a component. For instance, let's say you're working on a schematic and it calls for a 150 picofarad capacitor. Now, you go over to your electronics store and you go into their capacitor section, you start rummaging around for a 150 picofarad capacitor. But for the life of you, you can't find 150 picofarads. They've got picofarads, they've got nanofarads, they might even have microfarads, but that's an awfully large capacitor. And you're searching high and low, you can't find it. Well, they might not actually have 150 picofarad capacitors in your electronics store, but they might have a 0.15 nanofarad capacitor. And you come to that conclusion by just dividing by 1,000. And an easy way to divide by 1,000 is, you'll imagine that with 150, you've got a decimal point right there at the end. in order to convert picofarads into nanofarads, just take that decimal point and hop it 3 spaces to the left. And then you have 150 picofarads. Now, in the other direction, you just move the, if you want to figure out nanofarads to picofarads, you just move the imaginary little decimal point there to the right instead. And that'll allow you to make quick changes of notation. For instance, let's say you're dealing with a bunch of resistors, and when you've got them all added together, you end up with 150,000 ohms. Well, you know that if you move the decimal point this way, you can get rid of all 3 of those zeros, and you're just going to have 150 k ohms. So that's why we use engineering notation. It's very quick, it's very easy, and if your calculator is kind to you, it'll have a nice easy way for you to use engineering notation. Now, I'll just show you, I'm going to make up something on the fly to figure out, to use 2 different types of engineering notation in an equation, and I'll show you how it works. Let's say we've got a 470 k ohm resistor, and it is dissipating 230 milliamps. Now, we want to find out what the voltage is going through that resistor. So we'll go to our nice Ohm's law and remember that voltage equals current times resistance. So I'm just going to close my pen up here for a second while I reach for my calculator, which is actually my phone, but it works great and it shows up on the camera nicely, so that's a good thing too. So in the case of this particular app, when I want to take these units and I want to multiply them with each other, we're going to go 470, and we're going to hit the exponent button, and being as we know that k ohms is 1 times 10 to the third, we're just going to hit that exponent button and hit 3, and you'll notice it goes 470 times 10 to the third on the screen there. And we're going to multiply that by 230 milliamps, and you'll remember again that milliamps is 1 times 10 to the negative 3. Interestingly enough, these cancel out and we could just multiply 470 by 230, but we're going to take 230 times, and then we're going to hit the exponent button, which is times 10 to the negative 3 for milliamps, and we're going to hit equals, and apparently we are passing 108,100 volts through that resistor, which is, that's a lot of volts. And in this case, of course, we can condense that down to 108.1 kV. That's an incredible amount of voltage. And actually, that's an incredible amount of current as well when you're dealing with that much voltage. That's interesting that I picked numbers that gave me such a large result. You wouldn't want to play around with that much voltage. That would be exceedingly dangerous to mess around with that much voltage. So there you have it. That's just our little primer there on engineering notation. If you have any questions or comments, please let me know in the comments section below. I'll try to answer if there are any confusions. And if you liked the video, give it a share. Let your friends know about the channel, give it a subscribe, and I will see you in the next video.